Hello students, I'm here to bring joy to writing and solving a differential equation for a capacitor charging and discharging in terms of Q as a function of time. Now, what we have here is an RC circuit hooked up to an EMF, an electromotive force. It's going to deliver charge to the capacitor. We're going to take conventional current out of the battery as indicated in the diagram. So when we flip the switch to A, that capacitor fills up quite quickly in the beginning. But over time, it takes a little bit more effort by the EMF to get the last few charges on the capacitor, because eventually that capacitor is going to equal the EMF of the battery. And notice that they're kind of opposing each other. Okay. All right, so here's what we're going to do. We're going to set up a differential equation, and then we're going to solve it. All right, so we're going to apply Kirchhoff's rule, loop rule. Now, let me connect flip that switch to A. So I'm going to use a clockwise loop. And in that loop, I'm going to add up all the potential differences associated with each of the components, the EMF, the resistor, and the capacitor. So the sum of which are equal to 0, by the way. So the first element component is the EMF, and that shows up as a positive because I'm adding in the direction of the conventional current. So current leaving the battery shows up as a positive. Now, as the current flows through the resistor, we have a drop in electric potential. So that's going to be minus IR. Okay? And then we're going into the capacitor. Now that capacitor is filling up, it's accumulating positive charge in that upper plate. And since we're going opposite positive, that's going to indicate a negative potential. Okay, even though we're storing charge in that capacitor. All right, so that's going to be VC, and that's equal to 0. Now, because the current is variable, that is to say that the charge is differential with respect to each incremental differential moment of time, we're going to express I as dq dt. Okay. Now, the voltage across the capacitor, in order to proceed with this setup, do not solve first order differential equation with constant coefficients, I'm going to replace VC, okay, with Q over C, okay, owing to the fact that Q is equal to voltage times capacitance, okay, so I'm going to replace that. So Q over C equals 0. All right, so there we have a setup of a differential equation. Now, typically in the questions, it says set up but do not solve. Okay, we just set up, but we haven't yet solved it yet. The next step is to solve the differential equation. Now, here are the steps. First of all, that was step 1, setting up the differential equation. Step 2 is the separating part. So this is a separable differential equation. And the way we're going to separate it is through a set of algebraic manipulations. So essentially what you're going to see is me separating the dq from dt. So dt is going to end up on one side of the equal sign, and dq is going to end up on the right-hand side of the equal sign through a set of algebraic steps. So check this out. I'm first going to isolate dq by dt over r. I'm not going to skip too many steps because, for one, I want you to pay attention and also not get lost in this endeavor. My hope is that you'll be able to feel comfortable setting up and solving a differential equation, but for the time being, it's perfectly okay to memorize. Go ahead and memorize this. Okay. All right. My next step, I'm going to multiply both sides by dt, okay? And I'm going to divide both sides by r. I'm going to divide both sides by e minus q over c. Now, I said those 3 algebraic steps, and hopefully you'll follow me when I go through the next step. All right, so multiplying both sides by dt and dividing both sides by dr, I get 1 over r dt. Okay, all right. Okay, let's just write this. And that's equal to dq. Okay? It's part of the separation. My next step is to divide both sides by the quantity E minus Q over C. 1 over R dt is equal to 1 over E to the minus Q over C dq. Oh boy, we're almost there. Well, we're not quite there yet, but that's the separation part. Okay, so that's the separable part. Okay, we just separated our first order differential equation, getting it ready to integrate. Okay, so separable. That's what this differential equation is. Okay, now the next step is to integrate. Okay, so I'm going to throw an integral sign on there. We're going to integrate both sides. Now let's pick our limits of integration before we continue. The lower bound of the integral is at time equals 0. That's the moment we flip the switch to some time later. Not necessarily infinity, but sometime later. Because we're going to create an expression that gives us the charge on that capacitor anywhere between 0 and when it's full. Okay? And then we'll look at the merits when we graph that thing, just so you get to see what it looks like. All right. For the Q, the capacitor is not filled yet, so it's empty. So the Q is going to be 0 to some Q later. Okay, not necessarily the total amount of charge that's accumulated on the capacitor, but the in-between charge over time. Page 2. Here we have the integral on the left-hand side is pretty straightforward. That's just 1 over R t. So R is a constant, integral dt is t. Evaluated from 0 to t, Tn for t minus 0 for t. So it's just 1 over RT. However, the integral on the right-hand side requires a little knowledge and a technique of integration called a U substitution. So the integral on the right-hand side is of the form 1 over U du, which is equal to natural log of U. All right, U in this integral is equal to the EMF minus Q over C du dq is equal to minus 1 over C. So check this out. dq is equal to minus C du. So we need to place minus C in front of the integrand in order so that when we take the derivative of our final expression, we get back the original function. You've heard that before, but it's worth saying. All right, so the integral of 1 over e minus q over c dq is minus c natural log of u. But I'm going to substitute the EMF minus q over c back in. Okay, q over c. And we're going to evaluate that from 0 to q. Now, evaluating this integral, well, watch this magic. I'm going to divide both sides by minus c, just to kind of simplify that right-hand side. So why don't I do that now? That's going to give us minus 1 over r c t. Okay. All right. Evaluating natural log of e minus q over c from 0 to q. Q in for q. So we have the natural log of EMF minus q in for q over c minus the natural log of 0 in for q. So that's just the natural log of e. All right, you know your properties of logs. Log a minus log b is log a over b. All right, so that's natural log of e minus q over c divided by e. Okay, and that gives us the expression, the natural log of 1 minus Q over EC. Just doing algebra, just a little bit of algebra here. All right. Now, what we have here is the expression in log form, and we need to turn it into exponential form. Okay, so here's my favorite part. Know that natural log is aka log base e. Log base e of 1 minus Q over EMF times C. All right. Okay, watch carefully. So I'm going to take E, the base E. I'm going to raise it to the stuff over here on the left-hand side. Okay, so you're going to raise E. Okay. And then you're going to set it equal to this quantity, 1 minus Q 1 minus Q over EMF times C. Okay. So I'm going to do that step here and set it equal to. So E raised to minus 1 over RC T is equal to 1 minus Q EC. All right, let's do that. So we have E to the minus 1 over RC T is equal to 1 minus Q over EMF times C. All right, I'm going to go on to the next page. Page 3. Just a couple more algebraic steps. Before we do that, I just want to let you know that this Q on the right-hand side of the expression, that's really what we're going to solve for. That's Q as a function of time, by the way. All right, 2 more steps. Here we go. I'm going to add Q sub T over the EMF times the capacitance to both sides, and I'm going to subtract E to the minus 1 over RCT. So that's 1 minus E to the minus T over RC. Let's just express it that way. And then multiply both sides by EMF times the capacitance. So there we have it. Q as a function of time, the time that is allotted to the charge accumulating on the capacitor is equal to the EMF times the capacitance times the quantity 1 minus E to the T over RC. Okay. Now that has a special graph. It's exponential. It's going to top out. It's going to have an asymptote, horizontal asymptote, at the voltage of the source. Okay, because the capacitance is going to take on the same voltage as the source. All right. I'm going to follow up with a little clip of an actual capacitor charging. So there you have it. This is the equation that expresses the charge on the capacitor as a function of time from the get-go. Okay, folks, here I am in Capstone, and I have the fancy RC circuit board all hooked up. I've got a 3-volt potential difference, pumping electrons into this 330 microfarad capacitor in series with a 100 ohm resistor. So I just thought, show what it looks like in real time. So I'm going to click record and show the capacitor charging and discharging. There you go. And I thought I'd show you what you can do with this graph, especially when it comes to the capacitance time constant, tau equals RC. I'm just going to add a page here and then bring in a graphic that I screenshot from a previous recording. And so let's see, open image file. I'll just talk briefly about it. Desktop, let's see, where is it? I think that's it. No, not that one. Oh, there it is. Okay, so check this out. This is the capacitor charging, and here's the deal. The 3 volts that were applied to the capacitor, and the capacitance time constant is the amount of time it takes the capacitor to charge to 0.63 times the the voltage, or 63% of the maximum voltage. And that time, what I have displayed here is 0.035 seconds. So it takes 0.035 seconds for this capacitor to charge to 63% of its maximum voltage. And that's dictated by the capacitance time constant. And I discussed it briefly earlier, but if you substitute RC in for T, you get 0.63 times EC. And that's the 63% of the charge on the capacitor. But so here's the deal. I've identified the amount of time it takes for the capacitor to charge to approximately 3 volts, 63%, which is around 1.8 volts, and it's 0.035 seconds. Now, if you divide that by the resistance in the resistor, you get the value of the capacitor. Tau is equal to RC, therefore C is equal to tau over R. Not too close, but it's close enough. The capacitor, it's 330 microfarads, and this is giving us approximately 350 microfarads. So that's not that bad. All right, have a good evening.